Hello and welcome to part 2. So in part 1's video, we found that everything lands at the same time if we release them from the same height. So in this video, I will explain this phenomenon with a mathematical approach. So Newton's second law tells us that the force on an object is its mass times its acceleration, F equals ma. So for a free-falling object, ignoring the negligible effects of air resistance, the only force acting on it is the force of gravity. Now let's see. For object A, applying Newton's second law, we get m1g, which is the force, equals m1a1. And the m1 cancels out, so a1 equals g. Likewise for object B, where a2 equals g. So now we can say that a1 equals a2, because g is just a constant, it's the gravity of Earth. Now, let's use part 1's experiment to see whether the objects are accelerating with the value of g. On screen now, the red lines represent the distance fallen by the balls at equal time intervals. And you can see, the distance between each line is increasing, which means their speeds are also increasing at the same rate. So, to find what the uniform acceleration is, we need to use one of the equations of uniform acceleration. There are 4 main equations, which are often enough to find out most things about a particular motion. The 5th one is rarely used. So, what do the letters mean? Well, S equals the displacement, which is basically the distance moved by an object in a particular direction. U is the initial velocity, V is the final velocity, A is the acceleration which we are trying to find, and T is time. So, which one do we need to use to find the gravitational acceleration of the Earth? Let's take a look at our experiment again and see what variables we have available and then decide which equation is most suitable to use. So, before the balls are dropped, they are held at rest, so we know that u, the initial velocity, is 0. When they drop, they are accelerating by a constant which we don't know yet. When it hits the ground, the distance it has fallen is the displacement, which I measured to be 0.8 meters. The time it took to fall was 12 frames, and I recorded this footage with 30 frames per second, so the time in seconds is 12 over 30 seconds, which is 0.4 seconds. So, what have we got? We have S equals 0.8 meters, U equals 0 meters per second, and T equals 0.4 seconds. Now, we can see that the second equation is the most suitable. Okay, let's put the values in the equation. So we've got 0.8 equals half A times 0.4 squared. And we get A equals 10 meters per second squared. According to Wikipedia, G has an approximate value of 9.81 meters per second squared. So our experimental value was pretty close. So I can say that the acceleration of free-falling objects are equal to the gravitational acceleration. This proves that no matter how heavy objects are, they will land at the same time.